Thank you very much. It's a great pleasure to be here, and I would like to thank Yonuk Chong particularly for organizing this whole week and bringing experts together here in Korea to talk about quantum science. What's that? Oh, I don't need a pointer, that's okay. Just to forward, right? Next slide? Okay, good. So I want to start with actually a very simple question. What is the meaning of this word that we use in this week, right? Because you have to be a little bit careful that quantum is, of course, not defined very well, right? And so I like to do this in a kind of joking way and just look at what is a quantum material. And if you look in Wikipedia, at least this was 2 or 3 years ago, I don't know if it's still the same, what is a quantum material? It's a broad term in condensed matter physics to put under the same umbrella materials that present strong electronic correlations and or some type of electronic order, such as superconductivity, magnetic order, or materials whose electronic properties are linked to non-generic quantum effects, such as topological insulators, Dirac electron systems such as graphene, as well as others. That's essentially all of solid-state physics, right? So you have to be very careful. In this week, we specifically focus on what we call quantum-coherent phenomena, right, where we have T2 and gate operations times, as you heard from Daniel before, but there's also the world of quantum materials, which kind of competes with that definition of quantum. So a few years ago, my center is, I'm the director of an IBS center on quantum-coherent nanoscience at Ewha Women's University in Seoul, and so I wanted to find out what is quantum nanoscience, and so I invited a group of experts, including Daniel, who you see here, also Andrea Morello, his name was mentioned a couple times, just to see if we can come to some agreement what is quantum coherent or what is quantum nanoscience. And so we finally realized that we have to be careful with that word quantum, and so we specifically said that we want to define quantum coherent nanoscience, which of course is at the intersection of quantum science and nanoscience. And then the special meaning of the word quantum, of course, is related to quantum coherence, meaning you have a superposition of states, as you heard in Daniel's talk, and also entanglement between different elements, such as qubits. And on the nanoscience, you have, of course, 2 different types of nanoscience. You have the top-down assembly, which is all these systems like lithographically defined quantum dots, like you heard in Daniel's talk, or superconducting devices. On the bottom-up assembly, you have molecular nanoscience and also defects in materials such as a nitrogen vacancy center in diamond, right? So we can ask ourselves, for example, is a Josephson junction-based quantum computer, is that part of quantum coherent nanoscience? And the answer is not clear, but you heard in the morning session that most of the engineering that is going on in that field is actually on the micrometer scale. It's much bigger than the nanoscale, right? Of course, the Josephson junction itself is nanometer scale, right? And so not everything that is in our conference here, I would say, is quantum coherent nanoscience. Now, at the core of it lies some ideas about some usefulness that we have, a quantum coherent functionality. And there, of course, you have quantum sensing, quantum computation, also quantum communication and quantum simulation that you can actually use to perform interesting tasks. And of course, this week, most of us are focused on quantum computation here. Now, I want to give you 2 examples to contrast whether something is quantum coherent nanoscience or not. And let's start with the example that we heard in the previous talk by Daniel, namely semiconductor devices such as transistors. Of course, the transistors that you have in your devices, such as the FinFET transistor shown here from a few years ago, they are very much on the nanoscale. They are in the several tens of nanometer smallest dimensions. But they are not really quantum coherent. There's nothing that they want to exploit that is quantum coherent. On the contrary, quantum effects in such transistors are a detrimental thing, right? They give you leakage currents. That is part of the power consumption problem that you have in your laptop, and so they want to avoid that, right? But we heard, of course, some of the great work that is done in the field of these same transistors, where you have small areas of spins in these semiconductors. And here is a slightly older example from the group of Andrea Morello and Andrew Jurak in UNSW. So you have a silicon a spin in a quantum dot in silicon. This is an isotopically purified silicon to get rid of the nuclear spins, and then you can have beautiful Rabi oscillations, quantum coherent manipulation of that spin qubit here with a gate operation time on the order of 3 microseconds and a coherence time T2 here around 30 milliseconds, so that's 10,000 gate operations per decoherence time, right? So that's a clear example of quantum coherent nanoscience. So it refers to the previous talk, and I also want to refer to the two talks after this talk here. We have a talk by Mario Rubin, on molecular magnets and how they can be used for quantum coherent or for quantum computing. Now, if you look back at the field of molecular magnets, in the beginning, you had small clusters of these molecules specifically designed by synthetic chemistry to make a two-level system with two stable magnetic states. So this is more in the direction of data storage, right? Then people realized that there is quantum tunneling between these two ground states. This is definitely getting you in the direction of quantum coherent phenomena. But then, of course, Mario was an integral part of the work where you can actually perform qubit operations on a single molecule that you put in an electromigration junction. So you contact this with a 3-terminal device, and you can do Rabi oscillations and even the Grover algorithm that he and Wolfgang Wernsdorfer and other people performed. Right? So you can see that you can clearly take the same system and take it from the quantum, traditional quantum systems into the quantum coherent parts, and this is what we call quantum coherent nanoscience. So to summarize this process took us about 3 years from the initial meeting. We actually finally published a paper last year in Nature Nanotechnology to make sort of a definition for that term quantum coherent nanoscience. And I want to just read one sentence here. Although quantum physics dictates the behavior of nanoscale objects, quantum coherence, which is central to quantum information, communication, and sensing, has not played an explicit role in much of nanoscience. Right? And we are actually working on the aspects of nanoscience that fall into the quantum coherent manipulation. Okay, so now I want to take this a little bit towards giving you an introduction to our center at IWA. So what do we actually do? So we do a lot of work with quantum coherence and with superposition. We are starting to get towards entanglement, but we haven't actually proven entanglement yet. And on the nanoscience side, we are exclusively working with bottom-up techniques. So the opposite of what Daniel showed us, right, which are lithographically defined systems, so top-down assembly. We are starting from the atomic scale or the molecular scale and making devices based on that. And there I think we can say that we are a pioneer in what you might call quantum coherent surface science. Now, let me give you an introduction to one of the tools that we're using, because you'll hear a lot about this also from the next talk from Soo-Yeon Park. So how can we actually work with individual atoms or molecules? And we do this by actually putting them onto a surface and using, for example, a scanning tunneling microscope as shown here. I know that many of you are not experts in this, so I want to give a 2-slide introduction to this. The STM is a relatively simple tool. It consists of a metallic needle that you place about 1 nanometer away from the surface that you want to study. And that's close enough that electrons can tunnel between the states in the tip and the states on the surface. That gives rise to a current if you apply a voltage between tip and sample, and you can measure this current. And that current is very sensitive to the tip sample distance and gives therefore a high spatial resolution of this tip. You can then move your tip in the X, Y, and Z direction, basically make a robot, and that allows you to take images of the surface. So here's an image taken with one of our STMs. The scale here is relatively small. That's 4 nanometers times 4 nanometers, right? That's smaller than the minimum feature size of any current device, like a FinFET transistor. This is even smaller, right? But what you see here is a regular pattern of bumps. That's the surface of an MgO crystal here. And on top of this, you see 2 volcanoes. Those are individual iron atoms that we put on top of this, right? So we are actually working truly on the atomic scale with our tool. If we take such a surface and we zoom out a little bit, let's look at a factor 10 bigger area. You see that it's not all beautiful, meaning you have slight changes, different thickness of an MgO film, or we just have a bare metal here. But that's beautiful for us because it allows us to work on, let's say, 2 layers of MgO, 3 layers of MgO, and compare that to the bare metal. Right? So we can actually, with the STM, decide exactly where we want to work. Right? Now, The second thing that an STM allows you to do is do spectroscopy. And here I want to show the example of a molecular spectroscopy. Here is a VOPC. That is a spin 1/2 system, so therefore be a potential qubit. But how can we measure some of the properties of that VOPC? What we decided is to put that VOPC on a metal surface with a molecular decoupling layer in between. Therefore, the VOPC is decoupled from the metal underneath, and you can see here an STM topographic image. The bright feature there is a VOPC, and now you can also put your tip at 2 different locations on that VOPC and measure the tunnel current or the conductance here as a function of the voltage that you apply, and you see 2 clear peaks. Those are called the highest occupied molecular orbital and the lowest unoccupied molecular orbital, very typical things from chemistry, and they tell you something about the structure, the electronic structure of that molecule. This is ongoing work by one of our students. The third thing that the STM allows us to do is to build structures one atom at a time. We don't just want to use the structures that we can find, such as an isolated atom or molecule. We want to actually move them and build structures. And that's here's something I want to show you. We place our tip a certain distance away from here, a titanium atom in red, apply a voltage, and make the titanium atom hop. Then we can move the tip again, make it hop again, move, and make it hop. And if you do this well, like one of our students did here, you can actually make a movie where you hop the titanium, take a picture, hop it again, take a picture, hop it again, to finally arrive at a structure that Hong wanted to build here, and Suyeon will tell us more about that structure in the next talk, because it actually consists of 2 qubits that we have on this surface here. And so this, of course, I want to say that this is a pioneered work by Don Eigler at IBM, now over 30 years ago, but it allows us and other researchers to build atomic scale structures with ultimate precision. Now, our center is at Ewha Women's University, and I want to show you just a very quick movie on the construction of this. So Ewha actually built a special building for us, and in particular, it allowed us to make something that is specific to the requirement that we have, namely that we need a very, very low vibration level for our systems. Right? So let me skip that. So how do we achieve this? We start with a very thick base plate, 1.4 meter thick concrete here. Took 150 concrete trucks just to make the base plate for that part of the building. And then we put concrete blocks on top of that we float with air springs. So this is a very special design that you can only do when you first build a new building. And this allowed us to achieve vibration level as shown here in thick blue. That's the vibration level that we get in our system here, and it's in comparison to the purple line behind it, which is the Max Planck Precision Laboratory in Stuttgart in Germany, which is kind of considered to be the state of the art for the vibration level for those kind of labs. So I'm very proud and happy to say that we achieve the same performance here in our laboratory at Ewha. Now, then we can build our tools. Unfortunately, or fortunately, because I like engineering, we actually build a lot of the tools ourselves. So the scanning tunneling microscope is actually at the very base here in this tank. So here you can see the tip is sitting down there. The whole system is about 4 meters tall and is cooled down to liquid helium temperature and even a little bit cooler. Here's a picture during the construction. So this is a room temperature vacuum chamber. Allows us to make these clean materials and put atoms on surfaces. And then the actual STM is in a tank filled with liquid helium to cool things down. And this is work done by a team of Yu Chang-bae with students and engineering. Now, one of the real advantages that we have is that there is, as Mario will tell us probably, there is an infinite number of combinations that you can choose. Right? You have an infinite number of molecules you can put on a surface, and there's a finite but very large number of atoms you can put on a surface. Right? And so with this tool, we have the ability to actually tailor what we want to look at. And so here's an example of titanium and iron atoms, again on this thin film of MgO. So you can think of this like a Lego box, where you have, we've studied only 6 of these Lego blocks on this surface here, and that took about 10 years of work. This is very tedious work to do in practice, but it allows us to build structures where we put these Lego blocks together, and you can have red blocks and green blocks, making interesting structures, as Suyan will show you in a little bit, right? So I want to now switch to how can we measure the spin properties here. So the first I want to show you is spin excitation spectroscopy. So here we have a single spin, spin 1/2, sitting on a thin layer of magnesium oxide. If we measure the spectrum here, the energy on the x-axis and the conductance, DIDV, on the y-axis, at zero magnetic field, you don't see anything. It's a flat conductance. Basically, it's an ohmic contact. But if we apply a magnetic field, then you see something is happening. We get a small depression around zero bias here at 2 Tesla. If we go up to 6 Tesla, then we can see we have a flat bottom around zero bias, which is the Fermi energy, and a stepwise increase to a higher conductance at plus and minus 1.5 milli electron volts. And those are spin excitations. That's the excitation that an electron can make in your localized spin system by kicking the system from the ground state 0 to the first excited state 1. And that, of course, is split by the magnetic field, by the Zeeman energy. So this is a measurement that we can do of the Zeeman energy of an individual spin. And this was actually work I started when I was at IBM a long, long time ago. It's my first work on spins on surfaces, is to demonstrate the spin excitation spectroscopy. Now, we need to do something more. We need to actually make our tip spin polarized. We need to make our tip magnetic. And that's a really fun way that we can do this. Here you see an STM picture. We have 1, 2, 3, 4, 5 iron atoms on that surface and 1 titanium, actually 4 iron atoms. And the black thing is a defect on that surface here. Now, what we learned is that we can bring our tip very close to one of these iron atoms and then apply a voltage in the range of what is it, 0.6 volts or something like that. And that cracks the chemical bond between the iron and the MgO. And if you're lucky and you do this well, you can transfer the iron to your tip. And in particular, you can attach it to the end of your tip, to your apex, right? And if we then take that same tip and measure the spectrum on the titanium, so you can see in the image, the iron has disappeared, and you can see a slightly asymmetric step in the spin excitation spectroscopy. If we pick up another one, in this particular case, the step difference becomes bigger. Pick up a third one, pick up a fourth one. This tells us in this particular case that the spin polarization of this particular tip actually got larger as we picked up more atoms onto the tip. That's not always the case. This is kind of a particularly easy example of this. But this allows us to make a spin polarized tip, and now we can use that spin polarized tip to measure the spins on the surface. Now, this brings me to our core technique, which is related to what we're doing this week, namely quantum coherent measurement, which is to combine this spin polarized STM together with electron spin resonance, such that we can do Rabi oscillations and similar measurements. Now, in order to do this, we use the electric field between tip and sample, and we don't just use our DC voltage, we also apply a very high frequency there, namely a frequency resonant with the Zeeman energy, so several tens of gigahertz. And that allows us, under certain conditions, to drive a spin resonance in that spin. And this allows us then to get atomic scale spatial resolution together with a much improved energy resolution, as I'll show you in the rest of this talk. And so here's kind of the main message I think that I want you to take away from this talk. We can measure the electron spin resonance spectrum for a single titanium atom on MgO. You can see here at 1.4 Tesla, we have a tunnel current that is changing at about 34.5 gigahertz. And of course, that is extremely sensitive to the Zeeman level, the Zeeman splitting, i.e. to the magnetic field that is applied, right? So if we go from 1.0 Tesla, we are at 24.5, to 1.6 Tesla, we are at 39.5 gigahertz. You can see that the ESR spectrum of the spin 1/2 changes linear with the external magnetic field. Now, that's only one way you can use this. I want to focus a little bit here on the sensing application. So if you're very careful and you apply very small RF voltages and so on, you can look at the native line width that we get for this electron spin resonance. And so here we are at 25.68 gigahertz, and we see that the line width that we get, full width of half maximum, here is 3.6 megahertz. If you convert 3.6 megahertz into your favorite energy scale, this is about 15 nanoelectron volts, or for Mario, that's 0.17 millikelvin, right? So you can see, of course, ESR can be very sensitive to very small changes in the local magnetic field. And so if we do this on these titanium spins again, then you can see that here are 3 different examples of 3 different titanium atoms sitting on the same surface, MgO. And you can see the blue one here has 1 very strong ESR line, a single line. You can see the red one has 6 ESR lines, and the orange one has 8 ESR lines, right? So what's the difference between them, right? And the difference is something that Daniel talked about in the previous talk. That's the interaction between a nuclear spin and the electron spin, right? Because here we have 3 different isotopes of titanium, right? We just looked at different spins on the surface, and you can see naturally you have 7% of 47 titanium, which has a nuclear spin of 5.5. Therefore, you get 6 ESR lines. And you have 5% of 49 titanium, which has nuclear spin 7.5, therefore giving rise to 8 ESR lines, right? So this is a local measurement of the isotope nature of the atom that you have on the surface. Now, why does the nuclear spin show up as a split in this ESR spectrum? That's not so difficult. It's really very closely related to what Daniel showed us, right? It's the same thing, actually, except for here we have localized spins, right? Both the electron spin and the nuclear spin are localized. In Daniel's case, the electron spin was a band structure, was a itinerant electron. So the nuclear spin, in the simplest picture, you can think of this as creating a magnetic field that will change the total magnetic field given by the externally applied magnetic field and the field created by the nuclear spin. So it gets you a lower ESR frequency or a higher ESR frequency. For a nuclear spin 1/2, you would have 2 lines. If we have nuclear spin 7.5, we get 8 lines, right? And so that's actually why we see these 6 and 8 lines here. We can be sensitive to the nuclear spin. But the STM allows you to do more. And this, I think, is really the power of using scanning tunneling microscopy together with these types of spectroscopies. As I showed you in the movie that Hong made about the atom manipulation on the surface, you could see that sometimes the atom appeared tall and sometimes short. That's because there are 2 different binding sites. Now we are on the bridge binding site between 2 oxygen atoms, and we get the spectrum that I showed you before for one particular titanium here. But if we move it to the oxygen on top binding site, then you can see that the topographic image looks smaller, the atom appears kind of weaker, and the hyperfine interaction also is quite different. Actually, it's totally different. It's about a factor of 3 or 4 smaller, and actually is even more complicated. I don't want to get into this. If we now move back to a bridge binding site, we get back to this spectrum that we see before. And so finally, I want to ask the question, why is this? Why is there a difference in this hyperfine interaction here? This is now not what Daniel talked about. This is more what Mario will tell us about. This is more molecular type argument. And the argument is that in both cases, the titanium is in a spin 1/2, the electron spin is spin 1/2, but they are sitting in a different type of orbital. And I think here I'm still using the old orbitals, I think, which are wrong, right? But they have a different spatial orientation, and therefore they interact differently with the nuclear spin, giving rise to a different type of hyperfine interaction, which you saw in the see here between the red and the blue and the green curve. Okay, so this brings me almost to the end. I want to just introduce the next 2 talks. So we have one talk by Dr. Suyeon Park from our center, and he will show you how we can use these techniques to do quantum coherent manipulation, right? I showed you only CW ESR here, but of course we can also do pulsed measurements, and in particular we can do pulsed measurements on multiple spins, which I think is very exciting. And then Mario will take us to using the molecules to do quantum coherent manipulation on molecular spins. Okay, so in summary, at QNS we work on different types of materials, a little bit of work on point defects in materials, most of the work done with spins on surfaces, and that's either is atomic spins or molecular spins, such as this endohedral fullerene here. We focus always on discrete quantum states, so that's the classical type of quantum definition, but then we do coherent manipulations such as ensemble ESR or single spin ESR, and then quantum coherent manipulations, as you will see in the next talk. And this brings me to the end here. This is a picture taken before Corona. The last time we could have no masks on to take a nice picture. So about half the people are gone onto different jobs. But this is about the size of our center. Missing here is Suyeon, who's sitting here, Yu Chong, Yu and Yi. And special thank you to my former group at IBM, Chris Lutz and Kai Yang, who now moved on to be a professor in Beijing, and theory collaborator Joaquin Fernandez-Rosier. Financial support, as you all know, the Institute for Basic Science is the primary funding source that we have, but also a big thank you to Eva Women's University for the administrative support, but in particular for building the building, which actually was supported by Eva funds. And thank you very much for your kind attention.
Thank you very much. The floor is open for questions. Please, go ahead.
Thank you. The coherent operation will coming in the next talks we are expecting. But just before going to that, if you look at the backdrop here, it's quantum technology toward scalable. So if you remember the Michel Simon's work in Australia, they claim that they can go up to, say, 10 to 20 qubit scale. So it's a kind of scalable, I think, or I don't know. It's not about Michel's work, it's your work. So could you tell us about a little bit of vision to the keyword scalable?
Yes.
I have no doubt that you can make a kind of device or system that have kind of scalable, but actually the limit is it's the same to the superconducting devices. It's the measurement and control, the scalability limits there. So do you have any vision or idea?
Yes, so what I kind of hinted at is that what we can do is we can have control over electron spin and nuclear spin, right? That opens up a relatively big space. I don't know if Mario will talk about this, but they did work doing quantum coherent manipulation in a multi-qubit nuclear spin space, right? But we have to be honest, with an STM, the biggest structure that we've ever built was the movie The Boy and His Atom. There we moved about 10,000 atoms, not spins, on a very simple surface. We chose the simplest thing that we can do. There was 10,000 manipulations in that movie, right? So something on that order is in principle possible. You're definitely not going to make 1 billion devices with a STM in a sequential manner. That's not the point, right? The point what we can do is we can do very precise studies where we can actually look at what is this atom doing in this environment, or what is this molecule doing in this environment? How do these two atoms talk to each other? And can we utilize this interaction for some quantum coherent phenomena, right? I think in the end, my goal is over the next few years to maybe show something like 5 qubits, right? And as you can see from the silicon devices, you know, now it's taking off, right? Because you have a big community. But a few years ago, something like 5 qubits was still state of the art in silicon quantum dots as well, right? So I feel like it's worthwhile to invest some time and see where this goes. But I honestly don't have an idea how to scale to, you know, thousands or millions. That's really not the point, I think, for an STM type study. There's one over here.
Thank you for the nice talk. And what is the similarity and difference between entanglement and coherence? Could you tell?
They are essentially the same thing, but you should have asked Daniel about this, right, from a theory perspective. But superposition is the core quantum property that you have in a single qubit or a single spin system. If you have 2 spins, right, then you can have more than just superposition in spin 1 and superposition in spin 2. They can be correlated with each other in this quantum mechanical fashion. And so I always like to think that entanglement is the concept of superposition just extended to multiple qubits or multiple quantum systems. So very similar, I think.
Thank you very much, Andreas. concerning the ligand field, you have shown the titanium in different positions, yes? Have you ever tried, I suppose yes, to put something on top? This would be additional way to modify the ligand field, for instance, hydrogen?
Yes, that's a really great idea that, you know, we have our atoms that are exposed to vacuum, so you could attach ligands to this, like hydrogen or something else. The hydrogen happens to come naturally because we're not controlling that. Titanium really likes to have a hydrogen attached, we think, right? But it's not really what you want. You want to say, can I add a ligand controllably to this? And this was done by other people, not for electron spin, but actually by Klaus Kahn's people. I think Marcus Tönnies was one of the guys in that, right, where they show that the spin can change by addition. I think they put hydrogen on there kind of on purpose, and they can see that they can change the spin by adding a ligand, right? I would think it would be more fun to put on a different ligand like CO or NO, like you suggested yesterday, right? So in principle, that's possible. We haven't done it for these systems yet.
In the images you have shown, there's hydrogen on or not?
Well, I mean, from the STM, we can't really tell, right? It doesn't look like there's anything on there. Density functional theory says that this should be a spin 1 on this surface, but we see clearly a spin 1/2 behavior. So something is changing, which could be a charge transfer or something is attached. So we have weak indications, I would say, that there's a hydrogen attached.